All right, welcome back. In this section, we're going to look at the currents through a PN junction. So we've looked on a graph of current density versus voltage and shown this sort of dependence, where the current takes off exponentially with respect to voltage in the forward direction, and saturates in the reverse bias direction. So what we want to do in this section is figure out the functional form for the diode current and relate it back to microscopic mechanisms inside of the diode. So first, let's look at this qualitatively. On your N-type side, just outside of the depletion width, you have quite a few electrons. And remember that they're distributed in energy according to the Boltzmann distribution. So there's random thermal excitation of some of these up to higher energies. On the p-type side, we have a small number of electrons. So we'd call this NP naught. So this is the number of minority electrons on the p-type side. And then this larger number here is N naught, the number of majority electrons on the N-type side of the diode in thermal equilibrium with no voltages applied. So of course, this one is given by Ni squared over N naught. Okay, so similarly for the holes, we could see that there's a large number of holes here distributed in energy, and this we call P naught, and then a small number of minority holes, which we call P N naught. Okay, now, if we apply a tiny little bias, let's imagine that we clamp this side and we apply a little bit of forward bias. So what the forward bias does is work against the built-in voltage. So V forward moves this band up. So when it moves this band up, it'll do one primary thing. It sort of lifts this large concentration of electrons up in energy so that more of them, as they're diffusing around randomly, left and right, more of them will eventually diffuse across to the other side. So in fact, what you're sort of saying is, what's the probability of an electron having an energy that's high enough that it can go across the junction as a function of bias? So as I add more and more forward bias, what I'm doing is bringing more and more of this Boltzmann distribution with me. And if I apply enough bias, what you'll see is that a large fraction eventually makes it above this, this delineation line, where they can make it up the hill to the other side of the depletion width just by random diffusion. Because remember, in this region, the E field is working against the electrons. So this is random thermal motion overcoming the drift motion. So the key is that you're sampling a larger and larger portion of this Boltzmann distribution as you apply forward bias and bring that conduction band up closer to the conduction band on the p-type side. Now on the other side of the junction, the electron number doesn't change very much. If you apply a voltage, it doesn't really do anything over here. So an electron can be near the depletion width edge and diffuse back and forth and sometimes make it into the depletion width. If it does, it gets swept through. And really the key is that by changing the forward bias, we don't really change the electric field all that much. And so the current associated with this drift of electrons is about constant with respect to voltage, meaning that it has, it's not a function of voltage. Whereas the current, which is due to diffusion, is a strong function of voltage. This is exponential with respect to voltage. So this gives us our sort of physical or intuitive reasoning for why this total diode current takes off exponentially in forward bias. And it's because of the diffusion current across the junction and enabling a larger and larger fraction to be at a high enough energy that they can diffuse across by the application of that forward bias. The drift component stays rather constant, and now we'll look into how we can actually calculate these currents as a function of properties of the junction. Now we're going to start to actually calculate the currents flowing through the p-n junction with applied voltage. So here's our depletion width from here to here. And we're going to define the regions outside of the depletion width on the N and P sides as the quasi-neutral regions, or Q and Rs. The key to understanding the currents flowing through here is to consider the diffusion currents we just talked about. So remember, we have a lot of electrons over here, and as we put forward bias on the diode, some of these electrons start to make it across the junction and make it to the other side here. On this p side, they're minority carriers, so they're majority here and minority here. So in this region, when they get injected into the quasi-neutral region, we're going to have recombination. But we'll also have diffusion. So the E field is, the magnitude is greater than 0 inside of the depletion width, but the E field is 0 in each of the quasi-neutral regions. So what we want now is to use our differential equations, which tell us about the minority carrier dynamics. In the edge of the depletion width in the quasi-neutral region for electrons, and at the edge of the depletion width in the n-type quasi-neutral region for holes, where they're the minority carriers. So our strategy is going to be to try to find the boundary conditions for our ambipolar transport equation for minority carriers, with those boundary conditions being voltage dependent, and then solve for the currents that flow in these little regions just outside of the depletion width. Now, in order to calculate these currents, we need to sort of use our unbiased case as a reference. And we assume that the injected number of carriers is small compared to the number of carriers on both sides under thermal equilibrium with no voltages applied. So this is again using this low injection condition. So now we can use a little trick of balancing the currents for the thermal equilibrium case. So at applied bias is 0, we can say that the J drift plus J diffusion equals 0 for the electron currents as well as similarly for the hole currents. So if we write this out, the J drift for the electrons is going to be the conductivity, which is Q times mu times the N as a function of X times the E field as a function of X, and then minus the current density given by the diffusion constant N times d N of X dx. And I'm missing a Q right here. So if we substitute in the Einstein relation, we can relate these two things. So d over mu is kBt over q. And we can reduce this down and solve for E of X, and we get that E of X is given by kBt over q, known as the thermal voltage, times 1 over N of X times d N of X dx. And we can also see, if we just take one more step, kBt over q d logarithm of N of X by dx gives us the E field. So now we can go back to our Gauss's law expressions and remember that the voltage drop, the voltage difference across the junction, is going to be given by the integral of the E field across the junction. So remember we derived this at V equals 0. So now let's make an infinitesimal V applied, which is greater than 0, but we're going to still use this approximate equation. So what we're saying is that we're changing the balance between drift and diffusion just a little bit so that we can still use this expression approximately and then solve for what happens in the junction. So we know that if we integrate from 0 to WD of the E field, we had better get the total drop, the total voltage drop across WD. So if our total voltage drop is now equal to V built-in minus V applied, we can substitute this expression in, carry out the integration, and we'll get that V built-in minus V applied is equal to kBt over q times the logarithm of, now we have to evaluate the carrier concentration at these two positions, x equals 0 and x equals WD. So at the one edge of the depletion width, it's going to be the majority carrier concentration. At the other, it's going to be the minority carrier concentration. And so we can write these as the N on the N-type side over N on the P-type side. So again, this is the expression for zero bias. For our case of zero applied bias, let's go back here for a second. we can see that the built-in voltage is given by negative kBt over Q times the logarithm. With no bias applied, this holds. So when we apply a bias, we end up with an expression that, so inverting this, we can write that the N and the P naught side is N. So we're working at v equals 0, that holds. Now what we're going to do is say, okay, when we apply a voltage, now we're going to make this voltage not equal to 0. This quantity doesn't really change all that much because it's already a large number and we don't really do anything to the doping on this side by applying a bias. However, what we're going to end up doing is injecting some of these carriers across the junction. So we started here with a very small number, the minority carrier number, and we're going to carry some over there by current. So now this number of electrons on the p-type side is no longer so small because we're injecting them as minority carriers into the p-type side. And now we're going to allow our voltage to appear in this equation. So what we're going to do is say at the x equals 0, which we're going to take to be here at the depletion width edge, we're going to say that our number of carriers is, our number of electrons is given by this expression. Now we want to get the built-in voltage out of here if we can. So we look to this equation above, which is the equation that tells us what's going on with no bias applied. So what we can do is break out this into n and not exponential to the negative 1 over v thermal, where v thermal is given by kBt over Q. So this is our thermal voltage times v built-in, and then this is exp to the v applied. Now what we can do is a little switcheroo here, and we can use the relationship up here to substitute for this part of this expression. So we can express the built-in voltage over V thermal as the exponential of, let's just shortcut straight to that, how about it? So what we can see is that if we replace this grouping here, we can substitute that as n p naught. So in the end here, we have n p equals n p naught exponential to the v applied over v thermal. So it's really interesting that we started out with considering the concentration on this side of the junction, the electrons as the majority carriers. We inject them across the junction, and what ends up happening is that we reduce it to an expression where the minority concentration on this side is actually controlling the current. So we've gone through and derived our boundary condition, which is voltage dependent, for the minority carrier concentration on the p-type side of the junction. And we're going to now proceed to stick this into the ambipolar transport equation with the assumption of low injection and derive the diffusion current that flows on this side of the junction because of the introduction of these minority electrons right here. Okay, now we've derived our boundary condition, which is voltage dependent. And I've taken the liberty of turning our original PN junction around. So now this is the N-type side over here. And we're just going to focus on the edge of the quasi-neutral region adjacent to the depletion width on the p-type side. So from our last discussion, we were injecting minority electrons from the N-type side of the junction into the p-type quasi-neutral region right at the edge of the depletion width. And we showed that the concentration of those electrons is given by NP naught exponential to the voltage applied over V thermal. And again, V thermal is defined as KBT over Q. So what's going to happen here, remember that the E field is 0 in the quasi-neutral region. So there's going to be diffusion, a diffusion current of these injected electrons into the quasi-neutral region. But at the same time, they're going to be recombining with the majority holes on the p-type region. From our discussions of minority carriers, what's going to be relevant here is most of the action is going to happen over the minority carrier diffusion length, which is given by the diffusion constant for the electrons on the p-type side now, remember. So this is the diffusion coefficient for the electrons, minority electrons in the p-type material times the lifetime of those electrons there. So let's get our equation that we need to use. So from the drift diffusion equation for excess carriers, we can figure out that the second derivative of the excess carrier population on the p-type side is going to be proportional to itself divided by this diffusion length squared. And that comes from balancing recombination, which would be delta n over tau, with diffusion, and then manipulating and doing some algebra. So this is a nice compact form of the equation that we can use. So what we want to do now is figure out the actual current that's flowing because of this gradient in the minority carrier distribution. Okay, in order to do this, we have to express this delta n on the p-type side. So delta n on the p-type side is going to be delta n with voltage, NP with voltage minus NP V equals 0. So this is NP naught, this one. And this one is our expression which we just derived. So it's NP naught times exponential to the V applied over V thermal. And then we're going to subtract off this NP naught. So obviously, we can take out the common factor and get NP naught times exponential V applied over V thermal minus 1. And this is, we're saying this is occurring right at the edge of the depletion width. So this is starting to look like the diode equation that we want. In fact, this is the origin of the ideal diode equation's voltage dependence. So the current can be found from remembering that the current is going to be carried by diffusion here. So it's going to be J diffusion, and this is going to equal negative Q times the diffusion coefficient times the gradient of the carrier distribution, d delta n on the p-type side, dx. So this is actually the current that's flowing down away from the junction because of the injection of minority carriers here. Now let's actually look at this, this excess carrier distribution as a function of distance and start to evaluate this derivative that we need to calculate the current. So we're going to cheat a little bit and use our knowledge from earlier sections, which tells us that the excess carrier concentration, delta n p, as a function of distance, has to be delta n p evaluated at x equals 0 times exponential to the minus x over ln, where ln is this minority carrier diffusion length here. Now, this is our expression, actually, for exactly this concentration evaluated at x equals 0. So we can put this together and get that delta n p of x and voltage is now going to be given by np naught times the voltage-dependent boundary condition exponential to the V applied over V thermal minus 1 whole thing times exponential to the minus x over the diffusion length for the minority carriers. So this is our function. Now we can take the derivative of it, d by dx, and we get everything here being constant, and what we're going to do is pull out a negative 1 over ln. So np naught over ln, and then the same expression, same thing in brackets. So now we can calculate the current by simply multiplying by negative q times d times this. So we're going to put in d and a q, and we're going to erase this and say now our J diffusion is equal to this. Okay, so our diffusion current goes to 0 as all the carriers go away, far away from the junction. But the other thing we can think about is what's happening from the outside world. So from the outside world, if we want to maintain steady state, we're injecting these minority carriers here, these minority electrons, and they're recombining with holes. So the hole concentration is actually decreasing on this side. So from the outside world, we have to bring in some holes in order to feed those, in order to feed that recombination at this region right next to the edge of the depletion width. So the last thing we need to do is just figure out what the current is that's crossing through the depletion width itself. We've talked about what happens outside, and what happens outside with the recombination and diffusion of the minority carriers controls what happens inside. So at the end of the day, we're going to have a traditional current, which is going in the opposite direction of our electrons. So our electrons are going this way, our J is going this way. And this current for the electrons inside the depletion width is going to be given by this expression here, evaluated right at the point at the edge of the depletion width. So we substitute x equals 0 in here, this goes to 1, and we're left with this expression for the current carried by the electrons through the depletion width. We get a similar expression for the holes, and we just replace all these numbers with their corresponding values. So this is going to be Q dP P n naught over LP times exponential, same thing, voltage over V thermal minus 1. So now we've talked about the fact that there's going to be a current flowing through the diode carried by the electrons, as well as one carried by the holes. We've evaluated them both at the edges of the depletion width. And we're assuming now that the current inside the depletion width is going to be constant for both the electrons and holes. And what this amounts to saying is that there's no recombination inside the depletion width, so that our number of carriers that we inject, every single one of them makes it to the other side. So then we can go ahead and sum our electrons and holes, currents, and collect some terms, and we'll end up with the total current equal to Q times dN nP naught over Ln, and then plus dP P n naught over Lp, and then everything multiplied by this voltage-dependent term, exponential to the voltage applied over V thermal minus 1. So now finally we can simplify this into our familiar expression for the ideal diode current. And I'm going to substitute back in for V thermal so that we have the QV over KBT. And that means that this quantity in green here is our J naught term, our reverse saturation current. So let's look at this quickly. So this whole part here becomes J naught. Let's make a substitution here for the doping on both sides that it's going to help us out. So we can look at this NP naught and say NP naught is Ni squared over Na. And similarly, P n naught is Ni squared over Nd. Substituting those in, we get Q times diffusion of the electrons on the p-type side. And I'm going to pull out the Ni squared for both sides, Ln. So, in the end of the day, this is our J naught expression. at the end of the day, we see that it's actually proportional to Ni squared, as well as some constants here having to do with the doping on both sides and the mobilities and diffusion constants of the carriers on the minority carriers on both sides. So now I've used the magic of video editing to cut to the chase here, and we're going to look at the dependencies inside the expression for J0. So let's refer back to our IV curve just so we remember what J0 is. This is forward bias. This is reverse bias. So the J0 is the saturation current that occurs for reverse biases before any breakdown happens at much higher reverse biases. So it's this constant region here. And we look at this expression, we see that there's two contributions to it. There's one contribution that's coming from the p-type side, the edge of the depletion width on the p-type side, and another contribution that's coming from the edge of the depletion width on the n-type side. So we've got our p-type doping here, n-type doping here. Remember that these quantities, dp, lp, and dn, ln, these refer to the minority carrier diffusion lengths and diffusion coefficients on the n-type side and the p-type side for the electrons on this side and the holes on that side. Now, we remember that the ln is square root of d tau. So because the minority carrier lifetime appears in this expression, we can see that our J0 will get very small if our minority carrier lifetimes are large. So also, we can look at the temperature dependence. So all of these terms have slight temperature dependencies, but the one that's going to win is the Ni. So Ni squared is given by Nc, Nv. These are our effective densities of states, exponential to the minus E gap over kBt. So there's actually a very strong temperature dependence here. And this says that at high temperatures, our leakage current, or our reverse bias saturation current, is going to get larger, 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 exponentially with 1 over temperature. So if you want to make your J0 small, you go to low temperatures. Also, if you want to reduce your J0s, you want to make sure that your minority carrier lifetimes are very long. Okay, so there you have it. We've taken the detailed picture of carrier concentrations, both in the case without any voltage applied, and then approximated that when we apply a voltage, we can still use those carrier concentrations to determine the currents which are injected across the p-n junction to the other side where they become minority carriers. They start on the majority carrier side, for example, the electrons on the n-type side, and then they get injected as minority carriers onto the p-type side. Through carrying out all of those considerations, we eventually arrive here at the ideal diode equation. And we can identify the terms that go into J0 and then talk about what makes for low J0, which is generally what you need for high performance in any application of a diode, be it solar cells or rectifiers or any other function. J0 should be minimized for maximum performance. Okay, so that concludes our treatment of ideal diodes and the currents that flow in them.